All right, with all that knowledge of Chapter 9 of alkyne chemistry, let's take a look at a few practice problems. So this is question 9.29, and we're going to start with part D. So we want to start with 1-butyne, so 1-butyne, and we want to make 1-butanol is the name of this compound. I know we haven't covered alcohol nomenclature, but it's called 1-butanol. So essentially all we're doing is adding a hydroxyl to this carbon. So there's no way for us to go directly from an alkyne to an alcohol. We don't have a way to do that. But in terms of retrosynthesis, I know that if I had 1-butene, so if I had 1-butene, which is this compound, all I would have to do is an anti-Markovnikov addition of water across that double bond. So I'd use borane THF followed by hydrogen peroxide and sodium hydroxide. So then the question becomes, how do I go from here to here? Could anybody make a suggestion on how to get from 1-butyne to 1-butene? I'll take any suggestions. I think my chat might be frozen. Oh, no, it's not. I think it is. Yes. Sorry, my chat is acting up, but I can see what you wrote, Allison. I can see that you put ammonia in sodium metal. So dissolving metal reduction, that's absolutely correct. So what she said is this. She said, well, if you treat it with sodium and liquid ammonia, that's going to reduce it to 1-butene. But the beauty of this one is that there's no sister trans when you have a terminal alkene, right? Because you have two hydrogens here. So since there's no sister trans, you could use dissolving metal reduction, or you could use hydrogenation in Lindlar's catalyst. That will work too, okay? Either way works. So we end up with 1-butene, and then all we have to do is treat it with borane and THF. This is going back to your chapter 8 days, followed by peroxide and sodium hydroxide. All right, wonderful. Let's try E. So let me write it down here. So we're starting out with 1-butene again. I believe, yep, we're starting with 1-butene again. And this time we're ending up with a longer carbon skeleton. Here we go. So we've got a bromine up here, and we've got a bromine down here. Okay. Well, in this case, first of all, I've got to add 2 carbons because I'm starting out with 4 carbons and then ending up with 6 carbons. But I just want to think about retrosynthesis for a minute, because the only way for me to do the anti-addition of these 2 bromines would be to have as a precursor trans 3-hexene, which is this compound here. So I'd have to have this trans, because then I get the anti-addition and I'd have 1 ethyl group up and 1 ethyl group down like this. Okay, well then how am I going to get from here to here? Well, the first thing I need to do is to add 2 carbons to my molecule. So I'm going to take this and I'm going to treat it with sodium amide, and then I'm going to add ethyl iodide. So ethyl iodide, and that's going to give me this compound. Let me write it out like this. So I'm going to end up with 3-hexene like this. And now I think it's more abundantly clear how to go from here to here. If we want to reduce it to a transalkene, we have to use sodium metal reduction. So we use sodium in liquid ammonia, and that's going to give us the desired alkene, which is the trans 3-hexene. And then we just treat it with bromine. All right, we treat it with bromine, and you can choose a solvent or not. Carbon tetrachloride is a good one. Could anybody tell me why they didn't write plus enantiomer? I'm trying to think of the best way. Why doesn't it say plus enantiomer for this? Could anybody tell me? That's a good question. Why doesn't it say like plus En? If you're unsure, The answer is because it's a meso compound. Yes, thanks, Warren. Awesome. Awesome. That's amazing. It's not that easy to tell, is it? All right, but if you rotate this carbon-carbon bond right here, you end up with, and I'll just draw it down here, you end up with this, which is a meso compound. So since it's a meso compound, it doesn't have an enantiomer. Okay? I mean, you look at the way it's drawn here, and it's not abundantly clear that it's meso, but it is a meso compound. Let's take a look at F. So F is in the same vein, I would say. I guess they're all in the same vein since they're all part of the same problem, 9.29 F. So I want to start with the ubiquitous 1-butide. Seems to be the favorite starting material here. And I want to end up with this compound where I do have an enantiomer. So I want to do the anti-addition, so I have plus an enantiomer. So in order to make that to make that product rather, since bromination occurs via anti-addition, I would have to start with the cis alkene, like that. And I've got to add 2 carbons. So we're going to add the 2 carbons the same way we did in the last problem. We treat it with sodium amide, followed by, we'll use ethyl bromide this time. That will give us 3-hexyne. Again, like this. And then if we want to reduce that to the cis, we're going to use H2 and Lindlar's catalyst, like that. And it gives us this. And then we treat that with bromine and we do anti-addition, but this time you do end up with a chiral compound that can have an enantiomer. So carbon tetrachloride, just like that. So what I propose is that the first thing that we look at on Monday morning will be question 9.29, and we'll start with the first 3 parts. So we'll do A, B, and C. If you have any other questions that you want to go over, feel free to email me, or you can just ask me on Monday morning, and I'm happy to do that. And I'll probably pick a few other questions as well. So make sure to try all of the suggested practice problems that I have posted on Canvas.